Hello everyone, welcome to the lecture 60 of the course Diffusion in Solids. This is the last video of this course, and therefore I decided to have it as a revision lecture where we will quickly go through some of the concepts that we have covered in this. Let me browse you through these concepts so that you have a overall story and overall picture for the course, and I hope you have enjoyed viewing this course and learned a good amount of concepts about the diffusion and various aspects of it. And as we have already told that if you have any questions, you can further post it on forum. So this lecture will also help you to when you are going for your exams to summarize everything in a quicker way. So let us start. So we started the course with the fundamentals of diffusion. Of course, we also did a little bit of mathematical reviews of the concept. So we started with Fick's first law, which is J is equal to minus d dou c by dou x plus dou c by dou y plus dou c by dou z in the Cartesian form, and based on the equation of the continuity, which is dou c by dou t equal to minus del dot j. We derived the Fick's second law, which is dou c by dou t equal to del dot d dot del c. And if d is independent of concentration, then the Fick's second law can be written as d into dou square c by dou x square plus dou square c by dou y square plus dou square c by dou z square. This is equal to dou c by dou t. And we could write this equation in the cylindrical coordinates as well as the spherical coordinates, and which is depending on the geometry which you are solving for the Fick's law. These forms of second law can be used. So this is what we call as the continuum approach for understanding the diffusion. Then we applied these Fick's laws to the various conditions, various diffusion problems. So in the steady state condition, we saw that dou c by dou t is 0, and we could derive the simple equation for the concentration as well as for the flux. So you see that the flux is independent of x here, whereas the concentration is linearly dependent on x. Then we started taking several non-steady state problems. So for example, a sandwich geometry of thin film condition where the B is sandwiched between the two blocks of A. And here you see that the time profile, we saw that it changes. So earlier it was this, and then this height decreases, and the depth to which the diffusion happens increases. And we also saw that these are called infinite domain problem because the diffusion depth is much smaller to the as compared to the overall dimensions of the sample. That's why mathematically we define the limit or the boundaries as plus and minus infinity. So the solution for such a case is a Gaussian solution given by mb by 2 root pi dt exponential minus x square by 4 dt. Then we also saw a thin film case where it is deposited on the surface, where the solution looks pretty similar, Cb equal to m by root pi dBt exponential minus x square by 4 dBt, and this is how the graph looks like. Typically in the experiments we plot log Cb versus x square, and the slope gives us minus 1 by 4 dBt. We also saw the constant source problem where the source concentration is maintained constant at the surface, and this gives rise to the error function solution where it is Cxt minus C naught by Cs minus C naught is equal to 1 minus error function x by 2 root dt. So if you plot the graph, you see that the initial concentration is same for all the times, but the depth increases as the time increases. So this is a typical case for carburization in steel. And this quantity is constant. We saw that x1 square by T1 is equal to x2 square by T2 if the temperature and the carburizing atmosphere are same for the same steel. So this is also a useful relation several times in the industrial problems. Then we saw the diffusion couple problem where A, B and A, if there is a diffusion couple, if the gradient of B is not very large and if the diffusivity of B is extremely large, then we can ignore the diffusion of A and we can write Cb of x comma t is equal to Cb naught by 2, 1 minus error function x by 2 root dt. And this is how the profile gets developed. Then from the infinite domain, we moved to the finite domain where we took the example of the vacuum degassing and we could write the surface concentration is constant and the initial concentration is uniform, and we arrived at the solution which has this kind of expression C minus C naught by Cs minus C naught equal to 1 minus 4 by pi, and in the double sum, in the summation we have this term which is cos as well as exponential terms are there, and here the j varies from 0 to infinity. And we also try to solve the homogenization problem which has a similar looking solution. So in the homogenization problem we saw that initially there is a composition variation and then after a long time the composition reaches average in it is throughout. And in addition, we also demonstrated that the use of a software like Scilab, which is open access, and we also tried to see that how we can plot these equations in the Scilab so that you get a better hands-on feel if I change certain parameter, how the profiles look like and so on. So I do suggest that you keep using that, try that for several other equations as well. Then after the continuum approach, what we move to is understanding the diffusion from an atomistic point of view. So that is where we started talking about what is known as random walk. Okay, so because there are large number of particles, we saw that it does not move in a stepwise fashion, rather it moves in a completely random way. So we saw that the average displacements are not enough or not appropriate to describe this kind of a behavior. It is described by what is known as the root mean square displacement, which is equal to root n times lambda. For the true random walk, we saw that this summation of cos theta ij is equal to 0, which appears here. And we also saw that then this how this root mean square displacement or the mean square displacement is related to the diffusivity. This is what we learned through the Einstein Smuchowski relation, and the d is equal to mean square displacement by 6 tau. And if you evoke the relation between this and the gamma, then d is equal to 1 by 6 gamma times lambda square. So this is an important relation that comes. Then we talked about several diffusion mechanisms that exist in different types of solids. So this, whereas this direct exchange and ring mechanism has historical importance. This was before the Kirkendall effect, when people thought that defect do not play a role in the case of atomic mechanisms. Then we talked about the interstitial mechanism. So if the solute is very small and it occupies the interstitials in the lattice, then it can jump to another interstitial, and we saw that this is the interstitial mechanism. For the vacancy mechanism, we saw that this is applicable to the self-diffusion or substitutional solid solute diffusion, where the atom exchanges its position with the vacancy. So then we also saw the collective mechanism which are there in the glasses or in the amorphous structure. Here in the vacancy mechanism, we talked about a mono vacancy, but we also understood, we also saw that it is possible that a vacancy, two vacancies join together to form a divacancy, and their motion also can contribute to the diffusion. This is particularly more present at the higher temperatures. We also have seen that interstitialcy mechanism of diffusion, which is where a self-interstitial atom is involved in the diffusional process. This is although more prevalent for the semiconductors and for the ionic solids. Then we started understanding the temperature and the pressure dependence of diffusion, where it is described by Arrhenius type of relation. D is equal to D naught exponential minus Q by kBT or minus Q by RT, depending on the value or the unit of Q you use. And this is how a typical Arrhenius plot would look like. And we saw that, for example, the Q depends on the mechanism. So, for example, for interstitial mechanism, Q is equal to delta Hm, which is the enthalpy of migration, because interstitials are present everywhere. You do not need additional energy to create that defect. For the monovacancy mechanism, Q is equal to delta Hm plus delta Hv, which is the enthalpy of vacancy formation. So, this term gets added there. Then when we talked about the pressure dependence, we saw that it gives rise to what we known as the activation volume, because delta H is equal to delta E plus P delta V. This is significant at high pressures, but the effect is very less for solids at ambient pressures. So, this activation volume composes of two terms, minus kBT dou ln D by dou P at a constant temperature, plus a correction term which comes because of the correlation factors. So, the correlation factor itself, F, we called it as is equal to 1 plus 2 by n double summation cos theta ij, where the D star, the tracer diffusivity, is equal to F times D random. So, this correlation factor depends upon the atomic mechanism and the crystal structure. This is for example, for interstitial diffusion, the F is equal to 1, whereas for a vacancy mechanism, F is less than 1, and it depends upon which crystal structure we are talking about. So, we saw that this is cos theta I plus j average is 0, and therefore, F is equal to 1 here. For vacancy mechanism, it can be approximated to 1 minus 2 by z. For the interstitialcy mechanism, it is 1 plus average of cos theta, where this cos theta average is the average of cosines of angle between pair of correlated consecutive tracer jumps. While deriving this correlation factors, we also saw an important relation for cubic lattice, that cos theta I plus j average is equal to average of cos theta I plus 1 to the power j. This helped us in writing correlation factors for different cases. So, after the cases, after dealing with the atomic mechanisms, then we came to the interdiffusion, where the two metals or alloys, dissimilar metals or alloys come together in contact, and an interdiffusion zone is developed when this assembly is heated at fixed at any temperature. So, we saw that either you can form a solid solution. In this case, the interdiffusion profile is like that, whereas you can also form intermetallics where you can have a constant composition or slightly gradient, depending on whether the intermetallic itself is a line compound or a wide intermediate phase. The very important thing we saw in the case of interdiffusion, that because now the composition is constantly changing, we cannot ignore the dependence of D on the concentration. So, this D tilde that we see, it is dependent on concentration, and unlike the standard way of solving Fick's law, we could not take this D out of the equation. So, this makes the differential equation not ordinary, and because of this term that comes here. Then we also saw that the real driving force, although till now before this lecture we had seen that always we use the concentration gradient, but here in this concepts of interdiffusion we understood that it is the chemical potential gradient which drives the diffusion. So, in many cases the chemical potential gradient and the concentration gradient are in the same direction, but it is not necessarily so. The real driving force for interdiffusion is the chemical potential gradient. So, we saw this Onsager's relation Ji is equal to summation j equal to 1 to n minus Lij into dou mu j by dou x. This is the way to write flux when we want to relate it to the chemical potential gradient. We saw some key aspects of the phase formation in this interdiffusion zone, that the phases evolved can be correlated with the phase diagram. For example, you see here TiAl3, which is also present here in the phase diagram. However, it is not mandatory for all the single phase regions to be visible in the interdiffusion zone. So, we saw that the maximum number of phases that can form in a region in the interdiffusion zone, the P is actually equal to C minus 1. So, if it is a binary, you can have only single phase region here and so on. But not all the single phase regions have to be visible. So, in this example itself shows that in aluminum titanium you have several single phases possible, but what you see in the reaction layer is only TiAl3. The width of the reaction layer is not related to the width of the phase in the phase diagram. This is very important. This width is actually the kinetics. So you shouldn't think that if there is a line compound here, it should be like a line here. That this is a kinetics driven phenomena. The growth of this phase, thermodynamics only can tell us whether this phase can be there or not. We also had detailed lectures we talked about how to draw the composition profile for developed in the interdiffusion zone. So, we took such examples like magnesium, aluminum. You see that there is a gamma phase, there is a beta phase formed. So, if you see the phase diagram, then the gamma phase is a slightly wider composition range, whereas beta is almost like a line compound. So, therefore, in the composition profile you see that we have some gradient in the gamma phase, but beta is horizontal. So, depending upon the nature of the phase, whether it is a wide phase or a narrow phase, you can expect to see either a gradient or a horizontal line. So, we saw several such examples in the video. So, I definitely suggest you to practice on this as well. Then we saw that just now I also told you that the interdiffusion equation, because the D is not independent of concentration, it cannot be solved by standard methods how we solve the Fick's law. So, that is why for example, Boltzmann introduced this parameter lambda is equal to x minus x naught by root T, where x naught is known as the initial contact plane, also known as the metanoplane. So, this metanoplane x naught with respect to this, if you try to analyze for example, at x1, you see that at Cb star this particular composition, it moves as the x1 is changed and the time is changed, such a way that this ratio lambda, which is x by root T1, it remains constant. So, Boltzmann utilized this parameter to solve the differential equation, and we saw the derivation which finally yields that interdiffusion coefficient. So, remember, in this case we did not derive the concentration as such, but we derived the interdiffusion coefficient, which is equal to minus 1 by 2 T into the slope at Cb star into S plus R. So, the limitation here or the assumption here was there is no change in the partial molar volume. Then we talked about a very important Kirkendall effect, where Kirkendall conducted this experiment with copper and brass to show that these markers moved when this experiment was conducted out in the due to the interdiffusion, due to the unequal diffusivities of these elements copper and zinc. So, this marker shift was a seminal contribution in telling that the mechanisms of diffusion has to involve the defect. So, that is the vacancies, because otherwise you cannot explain these unequal diffusivities. And because of the unequal diffusivity, a corresponding vacancy flux has to be also present. And then we saw that the Kirkendall's experiment was analyzed further by Darkins, and Darkins equation gave interdiffusion coefficient xb into dA plus xa into dB, where dA and dB are the intrinsic diffusion coefficients. So, intrinsic diffusion coefficients are the diffusivities of A and B when a driving force is present. It is different slightly from the self diffusion coefficient where there is no driving force present. It is different from the interdiffusion coefficient, which talks only about the intermixing of A and B. So, these various diffusion coefficients we also need to remember what is the difference between tracer diffusion coefficient, self diffusion coefficient, and intrinsic diffusion coefficient, and interdiffusion coefficient. And if you replace, we can also further express this relation with respect to the tracer diffusivities, then a thermodynamic factor phi has to be multiplied. Then with the Manning introduced correction where the vacancy wind effect has to be taken into account. So, the Darkins equation was modified by multiplying a factor S, which is known also as the vacancy wind correction term. So, after understanding the diffusion, we definitely also talked about the CalFAD a little bit. We gave you the flavor of how we can computationally determine the diffusion profiles, how the CalFAD concepts are used in several softwares to predict the phases, to simulate the diffusion process. So, we devoted a little time there also. Then we moved to understand the principles of several characterization techniques which are used to measure diffusivities in various class of materials. We saw the tracer diffusion where sputter sectioning or mechanical sectioning, which is one of the most widely or you can say one of the most reliable ways of measuring tracer diffusivities. It provides a very wide range in which the diffusion coefficient can be measured. The only limitation being that the availability of the radioisotopes and a lot of safety concerns. We also saw the SIMS and EMPA, which also comes under the direct measurement technique. SIMS is more suitable for the lower diffusivities, whereas EPMA or EMPA is more for which is electron probe microanalysis. SIMS is secondary ionized spectrometry. So, EPMA is more suitable for the higher diffusivities. We also saw the NMR method, which comes both in direct as well as the indirect method. So, FGNMR you see is in the direct method, whereas there are some NMR methods based on the relaxations, which comes under the indirect methods also. We also saw the methods which make use of the mechanical relaxations or the magnetic relaxations, the internal friction on the diffusivity, and hence these are the indirect methods which are used to understand the diffusion coefficient. We also saw the concepts of Moss-Bayer spectroscopy and quasi-elastic neutron scattering, how these scattering relaxations can be used or to understand the diffusion behavior. And these two technique like MBS and QUENS, they are also sensitive to the atomic jumps. So, one can derive certain atomic jumps parameter using this technique. Then we first started looking at the other paths which exist in the crystalline materials, primarily the grain boundary. So, before that we only talked about the lattice diffusion. Then we moved to the grain boundary diffusion to understand the various kinetic regimes. So, where the grain boundary contribution is actually different at different temperatures. This is one thing about the grain boundary, that the way the grain boundary contributes to diffusion changes as you change the temperature. So, we saw in the type C regime where the bulk diffusion is extremely low, the diffusion takes place entirely through the grain boundaries. In such a case, you can have a grain boundary diffusion coefficient derived. In the very high temperature regime and very high annealing time, where the diffusion through the lattice and the grain boundaries are comparable, in that case you derive an effective diffusion coefficient, and there is an intermediate temperature where there is no overlapping of fringes, and in that case we have a distinct contribution from the lattice diffusion and from the grain boundaries, and in that case you can derive a triple product P, but essentially you can measure both the diffusion coefficient in bulk and in the grain boundary. We also saw examples, for example, in the B kinetic regime, you can see here that this is because of the lattice diffusion, this is because of the grain boundary diffusion. Whereas in the C kinetic regime, what you see is completely the through the grain boundaries. So in the C kinetic regime, you have a x square dependence. In the B kinetic regime, you have dependence on z to the power 6 by 5. The similar regimes existed also in the dislocation diffusion when we saw the difference being that instead of a slab here, it becomes a cylinder. So again, type A where you have effective diffusivities, type C where you can determine the dislocation diffusivity alone, the diffusion happens only through the dislocation, whereas in type B we can have both lattice diffusion as well as the dislocation diffusion contributing distinctly. And this was based on the Fisher model where the grain boundary was viewed as a slab, and what was taken into account is that there is in addition to the fluxes directly through the lattice and through the grain boundaries, there is additional leakage flux which goes from grain boundary to the grains, which makes the equations two-dimensional, and we saw I gave you a flavor of how complicated the expressions can get. We also saw these kinetic regimes later when we talked about the nanomaterials or the very fine grained, ultra fine grained polycrystals, where these kinetic regimes evolve as a function of time at a given temperature. So the various kinetic regimes which are distinguished by the parameters, basically the relative amount or the relative values of the grain boundary length, grain boundary diffusion length, grain size, or the bulk diffusion length, and so on. So this we discussed that this in nanocrystalline materials, this can evolve with time. Then we started talking about the diffusion in various classes of materials. We started with intermetallics, where there is a long range order must be present, and therefore makes the diffusion mechanisms very complex, like 6 jump cycle mechanism, triple defect mechanism, anti-structural big mechanism. And because in these mechanisms both the constituent species are involved, let's say in binary intermetallics, what it does is it gives rise to what is known as coupling of diffusivities, which means the diffusivities of constituents are nearly equal. We also saw that the order disorder transition that happens in certain intermetallics influences diffusivity. Typically, the ordered structures show high activation enthalpy for the diffusion. We talked about the metallic alloys where for the self diffusion, diffusivities near the melting point are very similar for most of the FCC metals in the range of 10 power minus 12 to 10 power minus 13 meters square per second. For BCC, they are an order of magnitude higher, and for the uniaxial materials like HCP and tetragonal systems, we saw that diffusivity has two principal components, one perpendicular and one parallel to the C axis. So interstitial diffusion, we already saw that it's a fast and no defect is necessary. We talked also about the solid solutions and the Hume-Rodri rules, and then we also understood that the impurity diffusion happens for the substitutional solutes by vacancy mechanisms. So we have a solute or an impurity diffusion coefficient. We saw some interesting trends also, like for example, in the aluminum, if we talk about, most of the transition metals have extremely low diffusivities than aluminum self-diffusion. So like this few trends we saw in the metallic alloys. In the open metals, the diffusion can happen by what is known as a dissociative mechanism. We also talked about diffusion in semiconductors, where the covalent bonding results in the high defect formation energies than metals, and hence the defect concentrations are orders of magnitude lower than what you see in the metals. And both vacancies and self-interstitials act as diffusion vehicles, and the dual mechanism gives rise to a variety of complex diffusion phenomena. Then doping is a common phenomena in the semiconductors. If you have N doping, that increases the negatively charged defects. If you have P doping, that increases positively charged defects. So P doping is done by adding group 13 elements, N is done by group 15 elements. And we saw that because again of the reasons mentioned above, that covalent bonding, the defect formation energies are higher. So the self diffusion in semiconductors is much slower than the metals. It is almost 4 orders of 3 to 4 orders of magnitude slower it can be. We saw a couple of examples also when we talked about diffusion in semiconductors. For example, the germanium self diffusion, this proceeds by vacancy mechanism, whereas in the silicon self diffusion proceeds by interstitial C mechanism, whereas the dopant diffusion by both vacancy and the interstitial C mechanism. And the diffusion coefficients for interdiffusion, interstitial diffusion in semiconductors are very high at the melting point in the range of 10 power minus 7 to 10 power minus 10 meters square per second. We also saw very recently the diffusion in ionic solids, where the diffusion is restricted to its own sublattice. In alkali halides, the diffusion mainly occurs by jumps of ions with the vacancy. So here is a table summarizing the diffusion in ionic solids, especially the comparison between the alkali halides and the silver halides. In one case, you have a Schottky defects present. In another case, you have the Frankel defects. The defect formation energy, for example, for Schottky is higher, 2 to 2.3 electron volt. For in Ag plus case, you have these Ag plus ions which are very mobile. The migration energies are very, very low. In the case of alkali halides, the main diffusing species are cation and anion vacancies, whereas in the silver halides it is Ag plus interstitials. And in the case of ionic conductivity, the cation vacancies contribute more due to their higher mobility in alkali halides. In silver halides, it is primarily due to fast moving Ag plus interstitials. Then anion diffusivity is via the anion vacancies, and in the case of silver halides, the anion diffusion is much slower than the diffusion of Ag plus interstitials. Then the temperature dependence, the vacancy pair diffusion is significant near the melting point. It decreases at the lower temperatures. And in the silver halides, the intrinsic diffusion occurs by interstitial C mechanism, which can have a jump sequence which is a collinear or non-collinear jumps. At lower temperatures, extrinsic vacancies also contribute. So actually, the extrinsic vacancies contribute at higher temperatures also, but in addition, at lower temperatures, you have the extrinsic vacancies forming complexes with the impurity. So that is an additional contribution. We also looked at some of the classes of materials such as high entropy alloys, which is a very new alloy design concept, while one of the core effect of high entropy alloy proposed was sluggish diffusion. But we discussed that this need not be a generalized concept, but it depends in addition to entropy on the elemental interactions also, other than crystal structure, temperatures and defect characteristics. We also briefly discussed about the diffusion aspects in quasi-crystals. where icosahedral quasicrystals we saw are highly symmetric and the diffusion is isotropic, whereas the decagonal quasicrystals are uniaxial, and D has two principal components, perpendicular and parallel to the decagonal axis. And in quasicrystals, additional point defects which are actually specific to quasicrystals known as phasons, they contribute also to a small extent. The phasons flip contributes to the self and the solute diffusion. And in fact, in this week itself, we saw the diffusion in glasses, where we understood that the structural relaxation in the glassy materials reached to the decrease in the diffusivity, initial decrease in diffusivity after it attains a plateau value. So, this time average diffusivity can be given as 1 over T integral 0 to T d dash dt. And here the diffusivity depends upon the thermal history and the technique of the glass production. So, at various points of time, especially when we were talking about some of the important concepts, as well as when we were talking about the diffusion in several classes of materials, we gave certain examples. Sometimes we only showed the concept by schematics, but what I strongly suggest to you is you can actually go to these papers. So, we have listed out several references for example, Metano-Boltzmann, Kirkendall, the Darkins equation, the radio tracer penetration profiles for ion beam sputtering, for these techniques of diffusion measurements like nuclear method, mass Bayer effect, diffusion broadening. You can actually go to these papers whenever you have some time, and this you can understand whatever is of more interest to you in a deeper way. So, here again some of the diffusion spectrum of metals. So, you can see the trend of diffusivities in metals, the Fisher model, the Harrison's classification, then about the dislocation pipe model, the various mechanisms of intermetallics which were proposed. So, you can see the original papers there as well. Then some more papers about the techniques, and finally it is also listed here some paper regarding a few papers regarding the diffusion in ionic solids. So, with this we end this lecture, and also this is the last video of this course. So, I really hope you have learned and you have enjoyed seeing the videos. So, any questions and feedback are always welcome. Thank you.